In this video, I will explain how to fit normal or Gaussian models and also Poisson models. But to do that, we will create a dataset first that we can export to SPSS Odds data. I will start by creating a project, same as in the previous part, and unlike the part 1, I will put this in a proper folder, not in downloads. And the name of the project will be part 2. Now this is asking us about creating a project inside a project. That's the workflow I decided to have, so that's okay. And now I will use the useR function to create a script. And my script will be 01 download and export. So that creates a new script. And I will load the trace statistics package. This is a package that connects to a website that I created many years ago, tracestatistics.io. And this package provides some functions to organize all the downloads and create a simple table inside R. I will also load the CEPI Geodist package, which is not on CRAN, it's on GitHub. I will also load the dplyr to do operations and combinations between tables, and Haven to export to SPSS and Stata, and also to read SPSS and Stata. So now the trace statistics package is okay, CEPI Geodist okay as well, dplyr nice, and Haven. Because CEPI Geodist is not on CRAN, install.packages won't work. You can go to GitHub and install from there. This is a very similar function. So then here you need to specify my GitHub username because I have that there, and the name of the package. That's it. So now we create a table with imports and exports between countries at aggregate level. So this will be aggregate rate from, let's say, 2010 to 2020. And here we use the OTS create daily data from 2010 to 2020, and we need to specify the name of the table, and this will be YRP, which means year, reported, and partner. And that function connects to my website, downloads everything, and combines all the years into a single dataset. And now we can export the table, and that's it. On the other hand, on the CEPI Geodist, we have a table with distances, common colonizer, common currency, etc. And we can use those variables to estimate a model. But there's a difference here. The distances table contains the ISO codes of the countries in uppercase, and the trade data has those in lowercase, so we need to fix that. So we type trade 20, then we insert the pipe, and then mutate. And then we can mute the reported ISO, for example. Reported ISO equals to upper, and then we specify the same variable, reported ISO, right? So if I run that, then I have that in uppercase. But I can also use a trick here. So if I expand my table, Here I can see that the imports and exports are numeric columns and the rest is text, and the year is an integer. That's a subtype of numeric. So I will use a mutate if. So I will indicate if is character, then to upper. That means if a column is of a text type, convert that to uppercase, and otherwise do nothing. So if I run that, now I have the reporter and the partner in uppercase. So now I'm almost in condition of joining the two tables, but this is a part of the documentation. So if you go to github.com and visit the repository for that package, you will see in the documentation that the distances table is written considering the minimum and maximum country. For example, if I have Argentina and Chile, because A goes before C, Argentina is the minimum. But then if I have Chile and Peru, Chile is the minimum. So here I will need to create new columns. So I will add a mutate and create a column ISO O, same as in the distances table. That will be the pairwise minimum between the two countries. So if I do that, I need the pmin function to get the minimum at a row level for all the rows in my dataset. So here I type reporter ISO and partner ISO, and then I create an ISO D, ISO destination with pmax, and same. And this is just to be able to join the two tables. And also here, in this case, I don't have blanks in the reported ISO, but in general, I can include an a.rm equals true, and that means to ignore blank values. So now I have this new column here. So now I will insert another pipe, and these two columns that also exist, ISO O and ISO D, also exist in the distances dataset, can be used to join my two tables with a left join that will just paste everything that exists in the distances table to the trade table, or I can use an inner join, and that will return the intersection. Why is that important? Before doing this, let me show an example. Let's say I have a table X with columns A containing values 1 to 3, column B with values, let's say, apple, orange, and banana, right? And then a variable, let's say S2, just to give a name, and this with values, let's say 7, 8, and 4. Okay, so now if I print my dataset, that's it. And then let's say I have a really similar dataset that contains, let's say, something like 1, 3, and 2, same apple, orange, and banana, right? And then another variable, let's say E3, with a value here an empty value, and here let's say that instead of a 3, here I have a 4. So now if I explore my table Y, here I have an empty value, right? And now if I do X pipe left join Y, then on my left side, in this case the table X, the combination 2 and orange has no match on the right side that is Y, because on the right side I have 4 orange. That's the combination. And therefore the result of the join returns an A for A equals 2 and B equals orange, and A equals 3 and B equals banana. Now I can try with something different. I can try with an inner join, and that's the intersection that I mentioned. So now this returns one single row, because those are the common observations. Both tables have in common A equals 1 and B equals apple. And I can do yet another operation, a full join. And that provides all possible combinations, even if those are not found on the two tables. So now I will conduct an inner join for the distances. And now I have created a table with the intersection of the two tables based on ISO O and ISO D. So now I need to overwrite my table, and that's it. So now I can use the use data function to save as R, or I can use save RDS that we also explored, but I don't really want that now. From Haven, I want to write as DTA, that's a data format. And here I can save trade 2010 as trade, 1020.dta. That's one way to export. And from Haven, I can also use the write function and write SAV that exports to SPSS format. That's it. So now my exercise will be to read this again. So let's say I read trade 1020 SPSS. So now with Haven, I don't need to write that. Haven : is just to see the functions easily. It's just that I can just type read underscore SAV if I know the name of the function, and that's it. And here I will read trade 1020.SAV. And now I've read that I exported to SPSS format, and now I read that back. That's one possibility. Now I will move to fit a linear model. So now we're in condition of fitting an OLS model, also a GLM model. So if we take the trade 1020 SPSS table, we can estimate, for example, an LM, same as in the previous part, and specify something like a log, and pass one of the flows, let's say the exports flow, log of trade value USD X, and let's say I just want to pass the distance as an independent variable, and then I specify the data that in this case is trade 2010 SPSS, or just trade 1020. It's the same. So if I run that, it doesn't like it because of NA values, right? So we need to subset this. So this is the first problem. I can specify the logs inside my function, or I can create a column previously to convert to logs. If I do that, the latter option, I can override my table and use a mutate to create a column that will be log of exports. And this will be just a log of the exports column. So that will create a new column in my table. And that's it. So now if I expand my trade 1020 SPSS table, now I have a new column with logs. And if I look here in the environment panel, I have a minus infinity values because some flows are zeros. So I need to be careful with that. How can I subset this? One option could be to specify the formula and then the data, and then put a pipe inside the LM function and type filter, and then filter trade value of exports greater than 0. And that by definition will omit any logged variable that contains infinity values. So if I try to run that now the model works, but I'm losing observations because I dropped all 0 flows. So how can I overcome this? One solution will be to use a zero inflated model, but to go to that, first I need to show you how to use a GLM with a normal or Gaussian link. So now here I will use the GLM function, right? So I can estimate by passing the logs inside the formula, like that, right? So that this estimates a GLM model with a Gaussian link. And in this case, the coefficient is the same as the coefficients that we obtain with the LM function. That's the OLS case. Or I can copy and paste my GLM function and remove the operation inside the formula and just call the column that I created with logs. And that's it. Also, now I can try to do something else. For example, I can either create a new column with the log of distance or pass the log inside the formula. I can put operations on both sides. For example, I can estimate log of trade explained by the log of distance inside the formula on both sides, and that works. Or I can pass log underscore distance inside the formula, then go up and create a new variable, let's say log dist, and that will be the logarithm of the distance. And I can also create another variable, let's say sq underscore dist equals the square of distance. That's it. So now I can go back to the GLM, and here I can use the new created column log of distance, and that will return an estimation. Or I can use square distance, the column, right? Or just square the distance inside the formula. But here I need to be careful. If I do that, in R, that's not the same as using the identity operation and then the square. If we look at that, we have a value that's different. The first case gave us something different, right? So why is that? Let's clear the console here. So we estimate with the identity operator, so we square something and then pass the final result to the formula, or we pass the newly created variable, right? So these two are equivalent because this column was already squared, and then we pass that column to the formula. But what if now we just want to square this directly? And this is not the same. Why is not the same? We can check here. It's not the same number because the square here creates an interaction of the variable with itself. So in R, for example, if I want to create an interaction, let's say between distance and common colony or common currency, I write a multiplication, and that's an interaction effect. So in this case, this didn't work because it's sorry, 1 second. The common currency here, sorry, it's not in this dataset, that's in another dataset, but we can use the variable common colonizer, for example, right? Or maybe the common language to provide something more interesting. So if this is the interaction between the distance and if the two countries share at least one official language. And if we do that, see what happened. We just wrote an interaction and R automatically included the estimated coefficient of the distance alone and the estimated coefficient of the common language alone and the interaction between the two. So going back to the previous example, to keep this simple, what's correct is to write the identity and then square, or to use a variable that's already squared. In this case, a column that's already squared. So now we can move to a zero inflated model. So now we can copy and paste, let's say, the squared distance to explain the log of trade. And now I can drop the filter and just pass the trade without a log. And here I will use the log of trade to think in terms of elasticity. And here I need to specify a family for a zero inflated model. And here I will use a quasi-Poisson. So that's a more general case of a Poisson. And this, in the econ theory, probably people from the economics field will know that the quasi-Poisson is equivalent to the Poisson maximum likelihood, or the pseudo-Poisson maximum likelihood that's widely used in international trade and in sanctions in particular. So now I will run this DLM with my quasi-Poisson. And now this works and doesn't complain about the observations containing exports equal to 0. And here I have my estimated model. Probably this is not the best model, but this summarizes how to fit models with R. So I will save this model. Let's say we will name this fit 0 because of 0 inflated. And now I can obtain a summary. And now I have the summary with the significance and the relevant information for my estimated model. So now probably I'm interested in saving this, so I can save my estimated model. So I will save my model here, and I will export this to a file, and that's it. In the next part, I will introduce fixed effects and what to do when we have a large number of fixed effects. But this is already a lot at this moment, so this is something to process, to retrace for yourself, and once you are ready, you can go to part 3. Thank you.